physics exam question that combines, well, a bit of year 1 physics actually, a bit of spring constants and dealing with forces in materials with simple harmonic motion. So it tells you there's two springs, A and B. It tells you the stiffness of both of them in terms of K, as in the stiffness of B is 3 times larger than the stiffness of A. It tells you that they're equal masses. It tells you that this whole system is connected to a generator, and the generator has a frequency of 2 Hertz. When the generator supplies energy to the springs move with a amplitude of this variable here, and they move with this much kinetic energy. It's then asking for the spring constant as well as the mass. So let's take this step by step. What I like to do in these questions is just make a note of everything we're given. So we're given the frequency of the generator, we're given the amplitude that the springs move off at, we're given the kinetic energy. We want to find the spring constant K. What it looks like we're going to use here is actually the conservation of energy, and it's very hard to spot this. But to find the spring constant K, I'm going to use the fact that the total kinetic energy that's being supplied from the generator to the spring is being transferred into the energy, elastic potential energy, of spring A, because it gives you the maximum kinetic energy of spring A that it oscillates with. So for the elastic potential energy, we're going to use a half kx squared, because that's the equation that involves the maximum amplitude or the extension, along with the spring constant which you're trying to find. And the kinetic energy is just given as 54 millijoules, which we're going to multiply by 10 to the minus 3 and convert into joules to use in calculation. We make that equal to a half k times the amplitude squared, which is 2.5 times 10 to the minus 2 squared. Great. From here we can say that the spring constant is 54 times 10 to the minus 3 all over a half of the amplitude squared. Now I'm just going to put that into my calculator and it'll give us a spring constant. 10 to the minus 3. Remember to only square the amplitude, by the way, and not the value of a half. Yep, that will get you 173 newtons per meter, sorry. The reason spring constant is newtons per meter is, if you remember Hooke's law, F equals kx, if you make k the subject, it's force divided by extension, so it's newtons divided by meters. Great. Now that we know the the spring constant of this spring, it's 173 newtons per meter, we can straight away find the stiffness of string B, because we know it's 3 times larger. So 3 times 173 is 518. So it's not 519, sorry. I took the exact value that I got from this from the calculator, which was 172.8 or something, and I multiplied that by 3. We also have to find the mass m. How we do that? Now we're moving on to year 2 content, so I'll change the pen color, and I'll just make a note that everything that we're going to do in purple is year 2 content. Might as well make a note that everything that we did in red is year 1 content. It's very hard to spot actually that year 2 is conservation of energy here. Now for the year 2 part, the mass, well, because we're given frequency, we're going to use that. The equation given for a mass on a spring system is 2 pi root m over k. In which case, because we know the frequency is 1 over the time period, I'm going to do the rest of the working out here. The frequency is the reciprocal of everything here. So it's 1 over 2 pi multiplied by root k over m. So for spring A specifically, it's 1 over 2 pi multiplied by the square root of the spring constant of spring A, which is 173, divided by the mass of spring A, which is what we're trying to find. Sorry. And we know the frequency of spring A is 2 Hertz because it's told the sign calculation. Okay, so let's go about rearranging this. First multiply both sides here by 2 pi. So 4 pi is equal to root 173 over m. Then square both sides. So 16 pi squared is 173 over m. And then you can sort of swap the positions of m and 16 pi squared to then obtain that the mass is 173 over 16 pi squared. I'm just going to do that on the calculator now. And I'll give you a value of 1.1 because the mass is measured in kg. And now we can move on to the last question. Calculate the frequency at which spring B oscillates with our maximum amplitude. So we're going to use that same maximum amplitude of 2.5 times 10 to the minus 2. So, and on top of that, we know the spring constant. We're just using the same equation again, honestly. So a frequency equals 1 over 2 pi multiplied by root spring constant of spring B, which we found is 518, because it's 3 times the spring constant that we previously found for spring A. And we divide that by the mass of spring B, which is the same as the mass of spring A, because it says 2 equal masses earlier on. It's a bit of a puzzle because it's given us so much information here, but let's put that into the calculator. (518 over 1.1), and your final answer is 3.45 Hertz. Perfect. Hopefully that all made sense, and if you have any questions, please let me know in the comments. That was simple harmonic motion mixed with a bit of materials. If you enjoyed the video, please consider liking it, subscribe, maybe with post notifications on. I'll post a video every day, at least one every day actually. I might post 2 some days, like today. See you soon. Bye.